welcome back. You might have wondered why this video is in English. Well, this is because this is actually a homework for a course I took on the physical theories of machine learning. Now, enough chatting, let's cut straight to the chase. As you have seen from the title, this video is about Gaussian Process Regression. Regression is the task of, given a few observed data points, here denoted by xy pairs, we aim to interpolate and extrapolate the xy pairs that are not observed. The most basic method is the linear regression, a very interesting topic on its own. In linear regression, we assume the regression curve is a line, say y equals ax plus b. Using least square error arguments, we can obtain the coefficients a and b via applying the pseudo-inverse onto the observed data points. This method can further be extended to obtain regression curves of higher polynomial orders. However, this analysis doesn't give us any information on our uncertainty of the estimates obtained. The Gaussian process regression aims to solve exactly this. Besides giving us a regression curve, it also provides us with the variance of each estimate. To put it another way, the usual regression techniques give us f of x, a deterministic value, while Gaussian process regression gives us a distribution over all the possible values of f of x. Now, let us dive straight into the math. Suppose we have n observed data points denoted by x1, y1 to xn, yn. We want to obtain an estimate on the endpoints f of x star 1 to f of x star m, where x star i's are not observed. The function f is the underlying true function that relates x and y. Let us list all the observed and unobserved data points into a single column vector. Gaussian process regression is a second-order regression method that assumes that this column vector follows a joint Gaussian distribution of this form. Henceforth, the name Gaussian process. The mean of the joint Gaussian is said to be 0, and the covariance matrix is partitioned into 4 blocks. The upper left block, K, is the covariance within the observed f of x's. K star star is the covariance within the unobserved f of x stars, while K star is the covariance between the observed and unobserved data points. The covariance matrices are defined via a special function called the kernel. As a side note, this kernel here is in fact greatly related to the kernel from reproducing kernel Hilbert space, and there are some really great videos explaining it. But for the meantime, think of it as a function representing the similarity between 2 points. A kernel should thus satisfy 2 properties: symmetry and positive semi-definiteness. Hold on, wait a minute. You might wonder, and you should wonder, why we can make such strong assumptions. Why can the mean be 0 and the covariance be defined by a kernel function? An explanation is that without any further additional prior knowledge, we should treat the mean to be 0 by symmetry arguments. Furthermore, as it turns out, with a well-chosen kernel function, the Gaussian process regression is in fact powerful enough to approximate the function f we want. So, the magic actually lies solely within the kernels. The choice of the kernel function relies on what kind of data you're dealing with. For data known to have linear relations, the kernel is chosen to be linear. For data known to exhibit periodic structure with period t, the kernel is chosen to boost the similarity of points that appear in integer multiples of the period. For our case, let us assume that, nearby points are highly correlated because why not? And the correlation drops off in a Gaussian tail manner. We thus use the radial basis function kernel as the generator of the covariance matrix. This function is parameterized by a length scale L and an output scale S. We will see the effects changing these parameters create till the end of the video. Continue on. The joint Gaussian distribution can be written explicitly as such. For Gaussian distribution, however, what truly matters is the terms inside the exponential. Thus, let us be lazy and remove the constants in front and replace the equality sign by the proportionality sign. As f of x's are observed to be the yi's, we can obtain a posteriori distribution on the f of x stars. Note that the denominator is irrelevant. We can absorb it also into the proportionality sign. Ideally, yi should coincide with f of xi. Realistically, however, there are noises within the observations, and yi is in fact equal to f of xi added with epsilon I, a zero mean noise term. Let us have the noises follow independent and identically distributed Gaussian distributions with known variance sigma squared. The prior distribution of the vector y1 to yn and f of x star 1 to f of x star m will then be the sum of the noiseless random variable and the zero mean noise. From the additivity of Gaussian random variables, we thus have the prior distribution as written here. Next, we know that the exponent is a quadratic equation in f of x star i's. It is required that we have an explicit form to the lower right block of the inverse of the covariance matrix. It is, however, mingled with the other blocks. Luckily, we have the famous matrix inversion lemma at our disposal. Plugging the terms of our covariance matrix into the lemma, we have the exponent written as such. We can then complete the squares and see that the resulting a posteriori distribution has mean m of xi and covariance matrix sigma of the following form. The vector m is our estimation of f of x star, and the covariance matrix contains the covariance f of xi star and f of xj star. The diagonal elements are special as they are the variance of f of x stars. And there we have it, the Gaussian process regression. This allows us to obtain the estimate of f of x star j as m of x star j, the jth term of the vector m, and with the variance sigma jj as the variance to m of x star j. It can be seen that the estimate is a linear combination of the kernels. This result reveals the intimate relation between kernel methods and regular linear regression. Here's a code example that I've written up in MATLAB. The blue curve is the real underlying function f of x. The red points are the observed sample values with noise. The orange curve is the estimate m of x star. And the orange shaded area is the 2 sigma confidence interval of our estimates. Now, this figure is obtained with s being 1 and l being 0.1. Next, with s fixed, let the length scale L be 0.05. We obtain this figure. You can see that the correlation between nearby points becomes smaller. One may ask what a suitable choice of the hyperparameters s, l, and sigma may be. A technique used to evaluate and learn the hyperparameters is to maximize the log likelihood function. This is the log likelihood of the parameters given the observed data points, and it can be optimized via a gradient descent scheme. However, note that there may be multiple maxima. To cap it off, the Gaussian process regression utilized a joint Gaussian prior to give us a Gaussian distribution of the estimated values. The mean of the joint Gaussian is assumed to be 0, and the covariance matrix is formed by the kernel function. The form of the data determines the kernel function chosen that best describes the similarity between data points. Lastly, the description above is obtained by taking the function space viewpoint. However, one can also take a parameter space viewpoint and using linear regression results to interpret it. And that's all for today. See you all in the next video.